we execute Microsoft Excel from our Digital Visual Fortran Integrated Development Environment, we see that it opens the HK workbook where we can start a new instance of our Visual Basic editor and insert a new module to write some declarations. I'll close this window and we'll begin by declaring the option explicit sentence, which matches the implicit known sentence of our Digital Visual Fortran DLL library. Also, it's a default that all arrays in Fortran are base 1, which means their first element is 1. There is no 0 element as it usually occurs in Visual Basic, so we'll use the option base 1 sentence at this point. Next, we'll declare our subroutine Heidemann and Khalil located in the Heidemann and Khalil dynamic link library file, and its arguments can be copied from Digital Visual Fortran to Visual Basic, and the only difference is that we need to specify the type, the kind of each argument in this sentence. The long verbal type matches the integer 4 variable type of Digital Visual Fortran. The same holds true for the flag variable, and the real 8 variable matches the double precision variable type of Visual Basic. We must also note that the mix variable is a matrix, but as it's gonna be passed by reference from one application to the other, it's declared in this sentence as an scalar would. The same for the CIJ matrix, same for temperature, relative volume, pressure, cubic term, and the QIG. And as we can see, the sentence is too long to fit on a single row, so we can make it a multi-row declaration to make our code more readable, and even use indentation to make it look cool. We are clear that the code that we are about to write in our Digital Visual Fortran DLL needs to be executed directly in a workbook. So we need to add a function which will be Q, as it will evaluate the Jacobian matrix, and it has as arguments a mixture range of cells, also a range for the binary interaction parameters, another one for the other binary interaction parameters, and the temperature will be a double precision variable, the same as the relative volume, and its result will be of varying kind. In the same way, we can make it a multi-row declaration. As every variable will be explicit, we'll declare the end variable as long, also the flag variable as long. We'll need a couple of index could be of the integer kind, but I'll use them as long kind to match the variable kind. We need a variable dimension matrix for the mixture of the double precision kind, one for the binary interaction parameter, one for the other binary interaction parameter, one for the QIG matrix, and a variable to be the return argument for pressure, one for the cubic term, and the temperature and relative volume are already declared in this function. We'll first assign n as the number of rows of our mixture range, rows property, count property, and we'll use it to redimension the mixture variable n by 4, which matches the fortran declaration here. Also the binary interaction matrix, the other binary interaction matrix, the Jacobian matrix, and pressure and C are okay. Next, we'll copy the values from our range of cells to our matrix variables. This one copies the mixture properties. This one copies the first binary interaction parameter. This one copies the second binary interaction parameter. And we have 2 for nested loops, so we need to close the outer loop here. Right after this, we can assign the flag variable as 0, and we have all the variables we need to call our fortran subroutine with the same name as the arguments it's using according to this tooltip here, which turns out to be very useful. Relative volume, pressure, cubic term, QIG, and all matrix variables will be passed by reference using their first element. Once Fortran receives the first element of this matrix, as they are being passed by reference, it will assign a return value of 1 just to let us know that everything is correct. Compile, we say that there's no errors, and this is the end of step 3.